I would like to show you today one of our systems, which is Wafer XRD 200. It is one of the systems in our product line for the crystal orientation with some difference. So as other systems, it uses Azimuthal algorithm for the crystal orientation, which is much faster and precise compared to the classical rock and curve method, which is time costly, which we cannot afford if we would like to do high throughput quality control of the wafer substrates. In this case, we can tell that this system utilizes the power of two different detectors and an algorithm that indexes the peaks that transversing detectors. And from these two data sets, we can calculate the crystal orientation of the wafer. The variety of different important parameters like the magnitude of the tilt, direction of the tilt, reference offset, and many more. Wafer XRD 200 system can be used for a variety of materials, variety of semiconductor substrates like gallium nitride, indium phosphide, silicon carbide, sapphire, and many more. This very system is set to silicon carbide, as silicon carbide is extremely important material, interest in which is skyrocketing nowadays due to its applicability in high power applications. So let's have a look at Wafer XRD 200 components. So first of all, we can see three different stages. For wafer cassettes, the instrument can contain from 3 to 5 wafer cassette stages. In the center of the instrument, we can see the handling robot moving the wafers from the cassette to the measurement table. It has two different pedals, and effectors if you wish. So in this case, the wafers can be measured in alternating manner, which speeds up the measurement process. A little bit further, you can see the measurement table with several sensors around it. The black box are the two detectors described in the Azimuthal scan method. Also, we can see the tube and sensors for the optical correction of the orientation of the wafer. Also, Cognex sensor pointed at the edge of the wafer is used. So while orientation of the wafer, we can reconstruct the wobbling curve and estimate very important parameters like wafer diameter and the geometrical parameters of the wafer feature. For example, for wafers containing flats, two most important feature parameters are the flat width and the flat depth. Such features can be measured with very, very high precision. We're talking about standard deviations of thousands and 10,000ths of a millimeter. Take into account the high throughput of the system and that the system is measuring hundreds of thousands of wafers. It's really important to identify every single wafer during the process of measurement. For that, the Cognex reader is installed, reading the barcodes or the wafer IDs, which goes to the final data sets. If we would like to start the measurement, first of all, we have to put the wafer cassette on the wafer cassette stage. The measurements are done in automatic mode. In order to minimize the influence of the operator, the process program are pre-created for the wafers of interest. For example, in this case, I'm dealing with process programs created for 6-inch wafers in order to measure the 25 wafers in the cassette that I just placed to the system. As we can see now, the robot is picking up the wafers one by one and moving them to the measurement table. The end effectors of a robot contains the vacuum chucks, so wafers are nicely secured during the handling. As we started the measurement, we can go to the measurement tab to see the results of the measurement. In the bottom right corner, we can see the signal from the laser sensor correcting for the wafer surface orientation. In such a way, we can deconstruct the wafer orientation as a physical object from the crystallographic orientation identified using the Azimuthal scan algorithm. The screen here contains three important subparts. The first one containing data sets from two different detectors, the gray one and the green one. The second one contains the wobbling curve measured by KN sensor. First of all, from the wobbling curve, it is possible to identify the diameter of the wafer and properly center it. The second, we can see the profile of the wafer feature. In this case, we are dealing with flats, so by mathematical processing of the shape of such feature, we can calculate important parameters of the feature. As I mentioned before, the flat width and the flat depth. The third one shows the laser correction curve, which is used to, as we can see, by fitting of this curve, we can understand what is the tilt of the wafer as a reflective surface. It was a brief introduction to Wafer XRD 200 system set for silicon carbide wafers of the sizes from 75 to 200 millimeters. As we also saw, the instrument provides highly precise and extremely fast measurements for high throughput quality control of silicon carbide wafers. Thank you for watching.